All right, students, what we'll be looking at today is continuity on an interval. So we're going to look at specific functions and their continuity. All right, so I'm just going to run through kind of a pretty long list of different types of functions. So to begin with, let's look at a linear function. Okay, what's the form of a linear function? What's the equation? Y equals mx plus b. Okay, so we'll just say f of x equals mx plus b. All right, now the thing is, you got to understand, well, what does a line look like? A line looks like a line, okay? It goes on forever in both directions. There's different kinds of possibilities. You could have a line kind of going like that. You could have a horizontal line going like that. Okay, the point is that there's no breaks in the graph. And if there's no breaks, where is it continuous? It would be continuous on all real numbers, so negative infinity to infinity. So anytime you got a linear function, you know it's continuous everywhere. Okay. Next thing's a polynomial function. Polynomial functions, remember, are sums and differences of whole number powers of x. That's why I like to say that in words. So the form would kind of be like this. We can have like ax to the n. Remember, n is some whole number, and then we can have another x to the n minus 1, dot, 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 like that. Okay? So it just goes on like that, and then you can have all the way up to x to the 0 power like that. So polynomial functions, remember, have different, there's 4 different ways they can look, what we've talked about. You know, you can have a polynomial that might look like this. That's kind of what it looks like if you have an odd degree. And it could look like this. That's another example of an odd degree polynomial. Even degree polynomials, what do they look like? They turn up. So you can have them kind of, that's an example of what even polynomial might look like. And here's an example, another example like that. So these two right here are the even degree that we've talked about. So again, are there any breaks? No breaks, nice and smooth. Okay, you can draw the graph without ever lifting your pencil, so you get the same result. You get that the polynomial functions are continuous on the interval of all real numbers. All right. So next thing to look at is rational functions, which we've talked about quite a bit. So remember, rational functions, I'll just kind of write this down here. They have the form r of x equals p of x over q of x. And remember what p and q are. P and q are polynomials. All right, now what happens on that is the key thing whenever you're looking at an algebraic fraction, really in general, you're looking at what makes the denominator 0. So we would say a rational function is continuous everywhere except any place that makes the denominator 0. And there's plenty of rational functions where the denominator is never 0. An example of that would be something like f of x equals 1 over 1 plus x squared. The denominator is never 0, so that would be continuous on all real numbers. But if you had something like 1 over x minus 1, well, that would be continuous from negative infinity to 1, and then from 1 to infinity, because x cannot equal to 1. So what we're saying on a polynomial function is it should be continuous anywhere except where the denominator is 0. Okay, and that's the way that rational function is always going to work. All right. Okay, we go to the next page. Let's see. I guess I was going to give a couple of examples, graphical examples of how a rational function looks. So you might have something kind of like this with an asymptote. And then, typically what we've talked about, what happens on rational functions is at the asymptote, they always go towards positive or negative infinity. So you might have something like that. There are times where you might have a polynomial look something like that. That's continuous everywhere because the denominator is never 0, and so forth. Okay, you might have more than one asymptote. We've certainly seen that before. So you might have something kind of like this. But the point on this is everywhere else it's going to be continuous. So this would be something you might see a polynomial sometime, or a rational function sometime that looks like that. All right. Okay, square root functions. Square root functions are going to have the form f of x is equal to the square root of x. Okay, really you can have a square root of some polynomial under it primarily. But what we're looking at is we're just looking at something like square root of x plus 1, really some sort of a linear function underneath the radical like that. So what you have to understand on this is square root of 0 is okay. You can get the square root of 0, you get 0. If you do the square root of a positive number, you get a positive number, so that's cool. What can't you do is, well, you can't do a square root of a negative number. Okay, so what you got to think about is whatever's under the radical must be greater than or equal to 0. So a square root function is always going to be continuous where the expression under the radical is greater than or equal to 0, right? So here's a couple of examples of how graphs might look on a square root function. So typically square root functions kind of look like this. Okay, and usually they're gonna be continuous everywhere the function is defined. All right, so a lot of times on a square root function, well, you won't have any values out here because it's making the radical, the number under the radical negative. Now, radical functions can look like this too. They kind of have that swoosh to it, like that. But the point is, you have to find the values that make the number under the radical 0 or positive. That's the idea. Okay. And the next thing, a root that is odd is continuous on all real numbers. So let me give you an example of that. So typically, if you had something like an odd root, if you had something like a third root of 0, well, the third root of 0 is cool. That's 0. You can do that. The third root of positive 8, that's 2. So you can do that. Well, cube root, odd root of a positive number is always positive. But what's a little different on an odd root than an even root is this. Okay, if you had the cube root of negative 8, can you get an answer? Indeed you can, yes, because negative 2 multiplied out 3 times would give negative 8. So that's okay. So actually you can do a cube root of any number, a fifth root of any number, seventh root of any number, and so forth. The graphs typically look like this. I'm just going to put this in the calculator real quick. If you go to the math button, that's where you can put your roots in. So like if I put in math and then option 4 is where you find the cube root. So if I just did the cube root of x in a standard window, you can see that that graph would be continuous everywhere. There's no breaks or anything. One other thing to show you, if you wanted to do like a seventh root, you go 7, math, and then you go down to option 5, like that. And then if you do the seventh root of x, the graph's going to look just about the same. Okay, it's kind of stretched a little bit, but it's continuous everywhere, like that. And if you did like an even root, like I'll say the sixth root of x, let me show you kind of what happens on the sixth root of x. Kind of looks like this. Okay, well, if you look at the sixth root, anytime you look at an even root, you're going to have all these errors because you can't do an even root of a negative number. Okay, so that's the way that works. You want to think about that and just understand how the arithmetic goes on that. So again, odd roots graphs typically look something kind of like this. Okay. All right, next thing is we've got the trig functions. So we want to talk a little bit about how the trig functions go. So the 6 trig functions are, we got the sine of x and the cosine of x. And those two graphs right there, they have kind of the same type of graph. You remember that's kind of the, that looks like that. It's kind of the wave function like that. Then we have the cosecant of x, and then we have the secant of x, the tangent of x, and the cotangent of x. And these things right here, they all have vertical asymptotes. Okay, so you're going to have lots of places on those 4 functions where it's discontinuous. You'll have an infinite discontinuity anywhere you have those vertical asymptotes. So first of all, the sine wave is continuous on all real numbers. Okay, let's just remind ourselves how the sine graph goes. You want to be sure that you review this and everything. So I'm going to put like pi here, 2 pi here, negative pi, negative 2 pi. You want to make sure that you go over and review your basic graphs. And the height, the max is 1 and the min's negative 1. So remember the sine wave goes like this. You have 0, 0, because you're on the unit circle. And just kind of a quick review here. Remember the sine is always the y value on the unit circle. All right. So I'll just kind of give you kind of a quick reminder of how this goes. So basically what you get is you get the sine of 0 is 0. The sine of pi over 2 is 1. And then you get down to this point, negative 1, 0. So you're back to 0 and so forth. You're down here, you're at negative 1. So you want to be sure that you remember this graph and how that goes. And it just cycles through these points. And the thing is, it's nice and smooth forever and ever and ever. So therefore, it's continuous on the interval of all real numbers. So that would be a graph of the sine from negative 2 pi to 2 pi. Okay, same thing happens with the cosine. So the cosine is also going to be continuous on all real numbers. And it's going to go like this. So let's just put together a graph just kind of for a quick reminder on how the cosine goes. Never want to forget these graphs because you're going to see these quite a bit in calc. So this goes like this. And remember the cosine is the x value. So if you go around the unit circle, you're just looking at those x values. So remember it goes like this. The cosine of 0 is 1. The cosine of pi over 2 is 0. Cosine of pi is negative 1. 3 pi over 2 is 0. And then you cycle through these points forever and ever and ever like that. Okay? So that's why that's continuous, because basically the idea on a sine and cosine is, since it's defined, the cosine's the x value on a unit circle, well, there's always an x value on a unit circle. There always is. And the same thing on the sine, there's always a y value on the unit circle. Okay, so that's kind of where that comes from in the unit circle. Okay, let's move on and kind of remind ourselves about the next trig functions. And this is just kind of a review. It's good to review this stuff and get this out of the way. So tangent, the thing that you got to remember on the tangent, and I think I got a unit circle I can paste up here real quick, for kind of a quick review on all these functions. So the thing about this is you want to make sure that you always remember the unit circle. You don't want to forget how to kind of quickly on the fly construct a unit circle, because in higher math, you know, all kinds of times in Calc 2 I can think of where you just need to kind of think in your head about where these type of functions are undefined. So I'm going to use this unit circle to kind of give us a quick reminder on how this goes. So the thing that you can't forget is the unit circle, and you can't forget that the tangent of theta is y over x. Okay, so if you look at this, there's places on here where y over x is undefined. So really you're looking at, well, where is x? 0. Because where x is 0, that's where the tangent's undefined. So if you look at this, okay, well, you got a problem there and you got a problem there. So pi over 2 and 3 pi over 2 would be two places where the tangent's undefined. So on the graph, I do want you to put a graph on here and just kind of remind yourself how this goes. Let's make this on our graph, let's make this pi over 4, this pi over 2, 3 pi over 4, and then let's go to pi like that. And then let's do the same thing over here. That way we'll go through about 2 periods of this graph. Okay, so just as a quick reminder, since you are undefined here, because the tangent would be 1 over 0 and negative 1 over 0, you're going to have a vertical asymptote here. And then I'm going to go this way. If you go this way, that would be negative pi over 2. So that would be the asymptote there. And then what happens is, Well, if you do y over x here, okay, so that would be 0 over 1. So the tangent of 0 is 0. If you do y over x here, y over x is 1. Root 2 over 2 divided by itself, of course, is 1. Like that. And then you may recall the tangent graph just kind of goes like this, and it goes to infinity on the left side of that asymptote. And if you go over here, at this point, at 3 pi over 4, y over x is negative 1. This divided by this is negative 1. Okay, so that would kind of go like this. This point would be at negative 1. I guess I need to label that as 1 and negative 1. And then the graph would approach the asymptote like that. All right. And then by the same kind of logic, there you have a point there that goes like that, and so forth. Okay, so this is how the tangent graph goes. You want to just kind of give yourself a quick reminder of how that goes and be able in your head to figure out where those asymptotes are. So what we're going to do on this is we're going to say where it's continuous, and you have to write a formula on this now. So what happens on this is there's a pattern. The asymptotes are pi over 2, 3 pi over 2. And then if you kept going, okay, this would be 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so forth. That just gives you odd pi over 2. Okay, so the way you would have to say this on here is you would say, and you have to kind of write this in kind of an unusual way. You could say, you could write this in several different ways, but if you were writing an interval on here, just to kind of get the pattern started on this, it would kind of go like this. And I think the best way actually not to think about this, to write this, would be, it would be continuous. Let's actually do this like this, okay? It's discontinuous at, and let's write a formula. Okay, so let's write this as, we're discontinuous at x equals k pi over 2, where k is a odd integer. But everywhere else it's going to be continuous. If you were actually writing this in an interval, you'd have to kind of say like pi over 2, and you would say oops, let me write this like this. You'd have to say like 0 to pi over 2, union, and then it would be continuous from pi over 2 until you get to 3 pi over 2, and so forth. So you just kind of have to write it out like that with the pattern going on forever, where this is, these are going by k pi over 2. All right, so that's how you could do that. Okay, I'm going to erase all these markings I made on this unit circle, and we'll just kind of do a quick review for the cotangent, how its graph goes. Main thing I want you to do is remember how to figure this out in your head, so you don't have to refer back to this all the time. So remember, the key thing is the cotangent of an angle theta is x over y. So the thought process becomes, well, where is y 0? If we can figure that out, we can figure out where the asymptotes are. So y is 0 at 0 radians and pi radians. Okay, so again, I'm going to just do this the same way. We're going to say it's discontinuous. We'll say at, and let's just write this down. So what you'd have is the asymptotes on a cotangent would go 0, pi, and then you would just keep going around pi, then 2 pi, 3 pi, and so forth like that. The pattern goes like this. This would be 0 pi, 2 pi, 4 pi, even pi. That's how I like to look at that. Over here you got 1 pi, 3 pi, 5 pi. In other words, you have odd pi. That's why I like to look at that. Okay, so what happens on this one, we're just going to write a formula. So this would be at even pi, and odd pi too. So you would have 0 pi, 2 pi, 3 pi, and so forth like that. So on this one, you would just say it's the cotangent's discontinuous at x equals k pi, and then you would say k is an integer. Now, if you're not familiar with this symbolism I'm doing, you'll see me do this quite a bit. That epsilon just means it's a member of the set. So I write that a lot of times this way. And then the symbol for an integer is kind of a Z with a double bar, kind of like that. That's how I tend to write that, is like that. Okay, so on the graph, let's see. Let's just do, let's go like this actually for the cotangent. Let's just do the kind of the same thing we did. And just so we can have in our notes a kind of a quick reminder of how this goes. Okay, so the cotangent graph goes like this. You have an asymptote at 0. You have an vertical asymptote at pi. You have one at negative pi. And so forth. And then the way I always kind of remember this is halfway in the middle of the asymptotes, you hit 0. To the left, and I need to really label that as 1 and negative 1, the points go like this. And you can refer and remind yourself of why that is on the unit circle. Okay, but the key for what we're doing here is just kind of getting the idea of where those asymptotes are and how you find those. Okay, so that's how that works out. Okay, well, what happens on the next things here is kind of goes like this. So the definition of a cosecant, the cosecant of theta, remember, is r over y. So it's the same thought process. It's, where is y 0? Well, that would be the same as the cotangent. Okay, so that would be at these values here, there and there. So actually what you would do is you would get vertical asymptotes just like you did on the cotangent. It would be 0, pi, 2 pi, blah, 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 and then don't forget about the negative ones out that way like that. Okay, so I want to kind of remind you. So actually, this one we'll just say the same thing. We'll just say the cosecant is discontinuous, and let's say at, and it'd be the same answer as it would on a cotangent, at x equals k pi, where k is a integer. Okay, and the way that you probably should have learned how to do a cosecant graph is like this. I'm going to just kind of remind you of how this goes. And again, you want to get these things memorized or be able to quickly figure this out. That's kind of the key. So I'm going to have you put like kind of a graph like this. And the way that you graph a cosecant is, since the cosecant is the reciprocal of the sine, a good way to do this is just to do the sine wave. So I'm going to just graph out the sine wave. And then we'll put in the asymptotes and kind of do a review of where the graph is then. So on this, the asymptotes always occur oh, I just graphed the cosine. I hope you guys didn't notice that. Okay, let me get that crap off of there. Okay, I just did a cosine. I should know better than that. There we go. Okay, so let's see. The sine wave goes like this. That's better. Okay. Okie dokie. Now we're in business. Okay, so that's what. Okay, notice the asymptotes occur at pi. See, y is 0. 2 pi, y is 0. At 0, y is 0, and so forth. Okay, so we want to get your asymptotes in. And then remember, the way this looks like is, it's kind of like, I kind of think of this as a camel, and it sits on the hump of the camel's back. Okay, so that's what kind of a cosecant looks like that, riding on the hump of the camel. All right, so that's how that goes. That would be how you would say the continuity on that. It's best to just say it's continuous on all real numbers except where the asymptotes are. Okay, and that's the idea. And the secant definition, secant of theta is x over r. Okay, like this. And so, not x over r, gosh. I need to think here. It's early in the morning. I'm not woke up yet. Need some coffee. Okay, so this is where x is 0. Okay, so where is x 0? Here and here, right? So basically this goes like this, and I'm just going to kind of remind you of the graph real quick on this, and we'll do the kind of the same thing we did on the last problem, and then we'll write the continuity on here. Okay, so you get everything kind of set up like that, and we graph the cosine. So the cosine starts at 0, 1, and then cycles through these points. Now, hopefully you got this down. I mean, this is stuff for calculus. You need to have your your trig down pretty well. These graphs are pretty important. They're going to show up quite a bit. And then what happens is the asymptotes occur at the same thing really as the tangent. Okay, so you got one at pi over 2, you have one at 3 pi over 2, and so forth. Okay, everywhere that, did I put, yeah, okay, I'm okay, x over 0. All right, so what we have on this then is the graph of the secant. Looks like this. Okay, and then what happens on this is, x is 0 at pi over 2, 3 pi over 2, 5 pi over 2, odd pi over 2. So you can just kind of think of this as odd pi over 2. So again, we're going to say the secant is discontinuous at x equals k pi over 2, where k is an odd integer. Okay, I kind of got going quick on that because I want to kind of get that's kind of review material on there. So that's what you have there. That's a quick overview that we needed to go through on the 6 trig functions and what their graphs look like. That's pretty important to do. Okay, so moving on, I'm going to run through some examples on here, and we'll just do these together, I think. Okay, so here's kind of what we're after on this. We want to be able to quickly recognize the type of function, quickly be able to figure out where it's discontinuous, and be able to write the interval where it is continuous. So if you graph y equals 4, you know that this is a horizontal line, so that this is a linear function. And linear functions are always continuous on all real numbers. There's no breaks in the graph on linear functions. Boom, problem done. Okay. This one, what kind of function is this? It's linear, again, okay, because that's y equals mx plus b form. And anytime you have a linear function, where's it continuous? Okay, good. All real numbers. All right. So that's how you want to get that put together. Okay. The next thing is, what kind of function is this? It's a ratio of polynomials, so it is rational. Okay, so the thing on this is, whenever you have a rational function, what do you focus on? You focus on the denominator and try to figure out what makes it 0. You're either going to have, vertical asymptotes or wholes, or you may have situations where the denominator is never 0. So on this one, it's just kind of a matter of doing your factoring. This one you could certainly do in your head. So the factoring for the difference of 2 squares is x plus 2 times x minus 2. No cancellation, so there's no wholes. So you basically just have a vertical asymptote at x equals negative 2 and another vertical asymptote at x equals 2. Okay, so what we would say is we're discontinuous at x equals, and you could even put plus minus 2 if you want to put that like that. And then continuous would just be like this. It would be everywhere except those two numbers. So you could say negative infinity to negative 2. That's to the left of that vertical asymptote. Then in between the two vertical asymptotes. And then to the right of the second vertical asymptote would be how you write that down then. Okay, so that's how you figure out the continuity of a rational function, right? Okay, next illustration is this one on the next page. Again, this is what kind of function? It be rational. Okay. So again, the whole thought process again is what makes the denominator 0? So we're going to need to do some factoring on this also. I'm going to leave the numerator as it is. The factoring of the denominator is x times x. For the 10, what do you use? You got two choices, 10 and 1, 5 and 2. You use 10 and 1 because you want the middle term to add to 9, so this would be actually x plus 10, x minus 1. Okay? Now, you do have a cancellation here, so you do have a whole. It's probably good to write down that you have a whole at x equals negative 1. Now, that is a place where it's discontinuous, so don't just cancel it out and ignore it. You would have to say we're discontinuous at negative 1. All right? And then you have a vertical asymptote. Remember, the vertical asymptote's the one that's left over. So we have a vertical asymptote at x equals negative 10. So this rational function would be continuous everywhere except these two places. Okay? And I think I don't know why I did that. Why did I put a negative there? I don't know. Okay, so let's see. We're discontinuous at x equals 1 and negative 10. That'd be better. Okay, all right. So let's see. Just write on this, our continuity would be everywhere to the left of negative 10. And then it would be everywhere to the right, in between the asymptotes, and to the right like that. Okay? All right. So that's kind of how you handle rational functions and their continuity. That's the thought process. Algebra required is some basic factoring typically. Okay, next thing we get to is what is this function? This is a square root function. And remember the thought process on this is what's under a radical can be 0. What's under a radical can be positive. What it can't be is negative. So what you do on this, the thought process is I need to figure out what value of x guarantees that what's under the radical is 0 or larger. So I solve the inequality 2x minus 3 greater than 0. Okay, well, go ahead and solve it. Well, you do, just add 3 to both sides. You can do all this in your head if you want to. So we get 2x greater than or equal to 3. Divide by 2. So you get this. Okay, so we would say that we're continuous on the interval bracket 3/2 infinity. Okay, like that. And then the continuity, see, I'm trying to do all these things as independently as the calculator as possible. If you are in doubt on these kind of things, you can look at your graphing calculator. So if I was to put in the square root of 2x minus 3, let me show you kind of what happens here. So the graph, notice that starting at 3/2, 3/2 is 1.5. So if I traced at 3/2, I get 0. And the square root of 0 is 0. So once you get beyond x equals 1.5, then you're going to have positive numbers under the radical, so you're getting square roots of positive numbers. When you trace to the left of this, you start getting nowhere. You just get nothing but things that are undefined. So there's no graph. Okay? So that's how that works out. Okay, the next one's also a square root function. This one's a little bit different idea. I'm going to show you how you could totally figure this out without a graphing calculator, but this is something you may not have seen, maybe in pre-calc or college algebra, so I don't know. But the idea is the same as the last problem. You start off by saying, okay, I need to figure out where that's 0 or bigger. So you work with the inequality, x to the second minus 9 is greater than or equal to 0. Okay? And when we do that, now you can't just do this. Sometimes students want to go x squared greater than or equal to 9. Not so good. Not so good. You have to do factoring, and you kind of got to analyze this a little bit. So what we're going to do is we're going to start off by solving this equation, which you can do by factoring, or yeah, you could do this. So just for variety, let's do this. Do the square root property like you learn in pre-calc or college algebra. So x is plus or minus 3. Okay, now what you got to do, and I'm going to go ahead and show this to you because you're going to do this a lot in calc. We're going to do what we call sign charts. And we're going to draw a number line, look at negative 3 and 3, and then all we're going to do is just do what we call test points. And we're going to do test points plugged into, we can just plug it in either to the factors. I'm going to plug it into the factors, I guess, so it doesn't matter. So if you factor x squared minus 9, we do that. So we're going to do test points, and we're going to see if we're getting positive numbers or negative numbers there. So let me show you how this works out and how you can analyze this. So what you do is you pick a number that's smaller than negative 3, like say negative 4, and then you plug into the function. All right, so what you would get is negative 4 plus 3 times negative 4 minus 3. Well, negative 4 plus 3 is a negative number. Negative 4 minus 3 is a negative number. And a negative times a negative is a positive, so that means we're okay. We're doing a square root of a positive number there. So that would tell us for sure we are continuous from negative infinity to negative 3, and then it's a bracket because when x is negative 3, you're due the square root of 0. Just think about that in your head. If x is negative 3, you'd have 9 minus 9 is 0. Square root of 3 is cool. Square root of 0 is cool, okay? All right, so we do that. Now we're going to do next test point here. Let's do a test point, let's use 0. Okay, plug in 0 into the factored form, or plug it into x squared minus 9. You'll get the same result. So this is 0 plus 3, 0 minus 3. That's a positive times a negative. That's a negative, so that's not good. So we're discontinuous there. So what I can conclude already on this, see, is I'm going to be discontinuous from negative 3 to 3. I got to, and remember at negative 3 you are continuous. So you've got that. Okay, now moving on from here. So the next thing I want to kind of look at here is what's happening past 3. So we're going to do a test point. Let's use something like, say, 4. And again, just plug in the 4. So you would have 4 plus 3, 4 minus 3. That's positive times positive is positive. It's okay to do a square root of a positive number. So that would tell us that we're also continuous from 3 and beyond. Okay, now that may be new to you. It just kind of depends on what kind of things you did in your previous class, but that's a good place in this class to get kind of started on the idea of using a sign chart to analyze a function. And essentially this just means that we're going to have we can do the square root out here and out here, but we can't do the square root here because we'd be doing the square root of a negative number. So let me show you what this would look like on the calculator. It's always a good idea, you're doing your homework, try to be as independent as your calculator as possible, but use your calculator as a checking tool and a learning tool because it's really an outstanding tool for this kind of stuff. So you put in square root of x squared minus 9. So it goes like that. Just do a standard graph, and you'll see this now. And this really shows what that sign chart showed. I mean, out here, you're continuous, 3 to infinity, negative infinity, negative 3, but you don't have anything going on out here. And I'll show you real quick, like if x is 0, if you did the square root of 0 squared of minus 9, you'd be doing the square root of negative 9. Therefore, you don't have any number there. The function has no undefined values, so there's no graph there. So that's how you would analyze that, okay? So again, square root function, the whole idea is figuring out where the function underneath the square root symbol is 0 or bigger. That's the idea. Okay, so let's see. Next thing here, this is a polynomial. And this one's real easy, okay? Polynomials, you just got to remember what do polynomials graphs look like. They look like that. They look like this, this, or this. Where are they continuous? Exactly, everywhere. Okay, so we got that. Very good. Okay, no graphing required on that. You want to know that. And by the way, this is an odd degree with a positive leading coefficient. So the graph of this thing would look like this. Okay, roughly. Okay. Okay, so this one now is an odd root. So if you have an odd root, then that just means you can do a cube root of a positive, you can do a cube root of 0, you can do a cube root of a negative. So it's continuous everywhere. Okay, and then this one would be just what we call a cube root function. Okay, these are really dealing with odd roots. Okay, so we don't have to graph. If you did want to graph on that, just to kind of verify, if I was doing my homework and stuff on this web work thing that we do, I'd just kind of do it the way I'm teaching you and then check it on your calculator before you put in your answer to save you an extra headache, okay? All right, so let's see. Let's go math cube root, which is option 4, and then x plus 1. And then we'll graph that. That's what it looks like. So see, that pretty well shows you it's continuous everywhere. Okay. Okay, so I think I'll close off here on this, and I'm going to have to break this part of the video up probably into 2 parts because I got to get into my office this morning. So I'm going to do these 2, and then I'm going to close off and post, and then I'll do the piecewise functions, continuity of piecewise. I'll do a little video for that, and left and right continuity, okay? Okay, so let's see. Now we're dealing with trig functions, okay? Well, this one's easy. It's a sine. No matter what happens on this, I mean, if you have period changes, phase shifts, whatever, the sine is still always going to look like that. So that's automatically continuous on all real numbers. And you could graph it in your graphing calculator, or just make sure that you're in radian mode when you do that. Okay, so here's the next thing. This is where it gets a little tricky. So the idea is, on a cosecant, this is the way that you would think through this. Okay, right now I don't know what the answer is. Honestly, I don't know what the answer is just without thinking, but my thought process is this. The cosecant of theta is r over y. So I got to figure out what makes this thing right here undefined, okay? So I'm going to be looking at it kind of like this. So I'm going to pull up my unit circle again and show you kind of what my thought process would be like on this and how you could do a kind of a quick calculation on this to figure this out. Okay, so the idea on this is the thing is you're trying to figure out where the sine of 2x is equal to 0. Not the sine of x, but the sine of 2x is 0. The 3 is just kind of stretching it. Like that's making the amplitude would be 3. The minus 9 is bringing it down. That doesn't have any bearing on this whatsoever. It turns out what matters is just this part right here that we call the argument. So if you haven't heard that before, the sine of what you're doing the sine of is called the argument. Okay, so the idea on this is we need to figure out where the sine is 0. The sine of 2x is 0. And let me explain that. I'm going to go back to this graph. And if you look at this graph of the cosecant, notice that everywhere the sine was 0, that's where you had an asymptote. Okay, so that's kind of what you want to look at is that part right here. So here's what I like to do in this problem then. Okay, so what I'm going to do is I'm just going to set that equal to 0. And then look at this on the unit circle. Okay, so here's what I'm going to kind of do on this, and this is how I like to show students this. Okay, where is the sine 0? remember the sine's the y value, so they've got these two places here. So this is what you do. You set the argument equal to 0, and then you set it equal to pi, because those are two places that make the sign 0. Now see, this has what we call a period change, so the vertical asymptote changes to a new location. So first thing I'm going to do is 2x equals 0, solve that equation, then 2x equals pi, and the result of these equations will give me two vertical asymptotes, and then that should be enough to figure out the pattern. Okay, so we just divide by 2 here, we get x equals 0. Okay, that's where a vertical asymptote is. Over here, we divide by 2. Now we have a vertical asymptote at pi over 2. Now all we got to do is find the pattern, because we have to write a formula on this then. Okay, like this. And the idea with this would be, you can see the pattern now. It's just going by pi over 2. But in case you didn't see that, okay, you've got 0, pi, the next place the sign of 0 is 2 pi. So you could go 2x equals 2 pi, divide by 2, well, you would get pi. Okay, so notice your vertical asymptotes on this then kind of go like this. You got 0, pi over 2, pi, then it would just be 3 pi over 2, and so forth. Okay, like that. So it would be at every pi over 2. Every pi over 2 is where that would happen. So again, I think the best way to write this is let's just say we're discontinuous at, and we would say x equals k pi over 2, and then this time k is an integer. Okay, so the idea with this is you look at the pattern again, it's 0 pi over 2, 1 pi over 2, 2 pi over 2, because after all, that's pi, see, 3 pi over 2, and so forth. It's all a matter of finding the pattern, and there's always a pi over 2 in this, but what changes is the integer values. So that's how I would figure that out. Okay? Okay, so the next thing is we want to look at the tangent. These are kind of tricky. Sometimes students don't have a very good background for this in a trigger pre-calc class, so there's kind of a learning curve to this. But my thought process on this always is unit circle, know it, know the definitions of the trig functions. So my thought process on this was the cosecant, the reciprocal of sine. Figure out what makes this argument 0, because if you do the reciprocal of 0, then it becomes undefined. Okay? So I'm going to need to erase this stuff. If you need to pause the video right now and kind of think about this a little bit, go ahead and do that. Now I'm going to erase this, and then I'll close off this video with the thought process that I'm going to go through on the tangent, which is actually very similar. Now once you get the hang of this, you'll be able to do this pretty quickly. Okay? So, on this one, the thing that you can't forget is the tangent of theta, just the basic definitions, y over x. So what you need to do is you need to figure out, the question on this is where is just the basic tangent of x undefined. Okay? The tangent is undefined where x is 0. So the tangent is undefined at pi over 2 and 3 pi over 2. So here's what you do. You do exactly what you did on the last thing. The argument, again, is this part right here. It's the tangent of 4x. And that's what tells you where the asymptotes move to, not the 2. The 2 stretches this graph vertically. So what you do is you set the argument equal to pi over 2 and 3 pi over 2, and you can go as far as you want to on that. But generally, if you can figure out 2 asymptotes, then you can figure out the pattern. So I'm going to solve the equation 4x equals pi over 2. Then I'm going to solve the equation 4x equals 3 pi over 2 like that. Okay, solve the equation, you'll get new asymptotes. So this one I'm going to, instead of dividing by 4, I'm going to multiply by a fourth. Okay, that's going to cancel that out. That's going to give x equals pi over 8. Okay, same thing here. I got to multiply by 1/4. Crosses that out. That's going to be x equals 3 pi over 8. Okay, like that. All right, now you get a nice pattern on this, and you can kind of, you can see this. It's 1 pi over 8, 3 pi over 8. What do you predict comes next? 1, 3, there you go, 5 pi over 8. Good observation. 7 pi over 8. So it looks like it's odd pi over 8. Odd pi over 8. All right. So again, we're going to say discontinuous at x equals k pi over 8. K is odd. That's how I figure that out. Okay. All the trig functions are kind of figured out in the same way. Try to get in your mind that what you do is set that argument equal to where a vertical asymptote is on the basic function. So if you did a cotangent, the cotangent has vertical asymptotes at 0 pi. So you set the argument equal to 0 and pi. Once you catch on to it, it's a piece of cake. All right, so I need to close this off, get this posted, and then I'll get the other ones up right away here as soon as I can.